You can print it, but you can't open it. Really?
I can open it.
Yeah.
But I can't do the edits for it.
Oh, you can?
I can.
And there's the graph in it.
Yeah. No, it's the better now.
What you could do is you could make the graph again and just print it on a separate page.
Also, I can write my question down.
Can you write it on a separate page? Yeah. Well, it'll have to do. It'll have to do. If this is what you have to do, then you should do this then. Yeah. Hey, anyone else? Anyone else? Do I have, except for you two, I will...
Hypothetically.
No, this isn't the time for questions. You can see I'm angry at some students.
I'm trying to help them.
Thank you. That's fine. Before 5 o'clock, it needs to be given to me. Not anyone else, but me. Okay? What? You gave it? You here? Yeah. Okay. So who? I'm waiting from 3 people, 4 people. Then. Where's yours? So yours is late. Am I going to get it today? Maybe. Well, if I don't get it today, tomorrow you lose 10%, and then it's 10% each day.
Of the 10% or 10%?
10%.
Okay.
You have 10 days.
Yeah, 10 days. Then there's no point. Am I collecting any more right now? No. Okay. Well, anyway, we'll continue now with the probability. Okay. Right. Can we see okay? I think so. Okay. Alright, so we're on to the next probability lesson now. The first one was just basic stuff. I can't remember what the next one is. Let's have a look. Is the next one tables or is it something else? Let's see. Yeah, tables. Okay. Let's have a look here. Right, so I turn the light on. So last time in probability we were looking at using sample spaces for calculating probabilities. Remember that? So what we're going to have a look at today is using tables for calculating probability. So I'll give you an example to get you the idea. Let's see. Okay. Is this working yet? Not yet. Okay. Now we're working. Right, so we're looking at using tables. So let's take a table like this, for example. Right, so we'll have, let's see here, and I need one more row actually. Okay, so what we're looking at now is if our information is in a table, how we can use that. So for example here, male, female, smoker, and then non-smoker.
Oh, this is like the DNA.
Fast smoker.
Table.
Actually, we'll just start with 2 to begin with, rather than with 3. Yeah, we'll just leave it with 2, but I'll put an extra one in here. Okay, so this table is just a collection of information. You would have seen stuff like this probably in biology as well. So we'll say that in our group of people, we'll say there are 20 men who are smokers, and then 10 women who are smokers, and then we'll say for non-smokers there's 30 women, we'll say 10 men who are non-smokers, and then for women we'll say there are 30 non-smokers. So this table really, there's nothing special about this table, but we're just using it for calculating probabilities. So if I was to ask you something like a question like how many men or how many women there are, well, before I can even answer any probability questions, I need to know the total. So this is why I left some boxes blank at the side here. It's for totaling. Example here. So here's our first example. In black is what we were given, and then in red is what we can add in. So we know if there's 20 men who smoke and 10 women who smoke, in total how many smokers are there? 30. And if there's 30 women who smoke and 10 non-smokers and 10 men who don't smoke, then there's 40. So there's 30 smokers and 40 non-smokers. So in total, how many smokers and non-smokers? 70. Now there's 20 men who smoke and 10 men who don't smoke. How many men are there? 30. And there are 10 women who smoke and 30 women who don't smoke. How many women? 40. Now do you notice that if I add these together, I also get 70? And the reason is, this is the total as smokers plus non-smokers, and the total as men plus women, and of course it should be the same, because everybody is either smoker, non-smoker, or male or female, so it makes sense that the total here and the total here will be the same. And in fact it's always the same. So you can get this 70 by adding these two, or by adding these two. Yeah. Now, it's just in my example, it was a coincidence that it was also 30-40 and 30-40. It won't really be like that. It was just a coincidence that it was the same numbers here and here. Okay. So now that we have our table drawn, we can answer some probability questions. So let's have a look at some probability questions. If I was to pick somebody from this table, what is the probability that they will be male? Well, what is the total? 30 or 70? 70 is the total. And then how many are outcomes I want? 30. This 30 here, there are 30 men. There's 70 in total. 3/7. Let's answer some more to practice here. So we'll say probability of female. What would that be? 40/70, which is 4/7. What about something like probability of male and smoker? What would that be? 20 over 70 still. 2/7. What about if I said something like probability of smoker? What would that be? 30 over 70. 3/7. See how we're using the table here? Yeah. Let's do an example of another one, but a little bit more difficult now. Actually, let's just do one more from here. Let's say probability of male or smoker. Well, it'll be over 70. But what would it be? On the top, it'd be 20 plus 10 plus 10. Now, the first 20 male smokers. The second 10 is just the 10 men who don't smoke. Because I said I want a man or a smoker. So that means I'm looking for the males and also the female smoker, yeah. So I'm looking at these three boxes here. These are the males or smokers. Basically everybody except this box, the female non-smokers. So the answer will be 4/7 then. So just be careful with the or. It usually involves adding. Usually. So this is just a basic example to show you how you can use these tables, but we'll look at more difficult ones now. So if you can just write that one down. Okay, do we have this? Yeah? Okay. Right, so let's have another table here. So again, split this up here. We'll say again male and female, and we'll have again 4 here. Whoops. And this one here will say 4, 12, 24, 10, 6, 14, 14 and 50. So what I'm doing here is I'm leaving some of the boxes out. Oh, and sorry, on the top, let's say these are grades. A grade, B grade, and C grade, and then we can have male or female, and then the last row and column is the total, as you know. Total, and then total. Okay. So what I've done is I've deliberately left some of the numbers blank, but there's still enough here to work out what the missing numbers must be. So before we answer any questions, I'll let you try this for a couple of minutes. I want you to figure out what the missing numbers should be. Should only take a minute or two. Okay, we have this? Yeah. So we know here the total is 24. 12 and 4 makes 16. So this has to be 8. And if this is an 8 and this is a 6, this has to be 14. And this makes 28. Well, it should total up to 50. 22, isn't it?
Yeah.
If this is 22 and this is 12, this has to be 10, and 10, 6, and this makes 26, and that does also add up to 50 then.
That's a good stuff, probably.
That's Sudoku puzzle, maybe. Right. So here's some questions. We'll start off with some easy ones, but then we'll make them a bit more difficult. So, first one I want everyone to calculate is, in this class, what is the probability that a student will get an A? This class? No, it's quite low in this class. In this class here, what's the probability of getting an A? We got this? Yeah, so it'll be 14 over 50, which is 7 over 25, or as a percentage, 28%. Okay. Yes. Try this one. In this class, when you pick someone at random, the probability that they'll be female. So, what's this one then? Part B. We'll get to it bit by bit. This is my 5th class today. I'm so low on energy. Is it?
Yeah.
Yes. But it's much worse for me than it is for you, trust me. Right, female. $26 over 50. Yeah, and as a percentage, just 52%. Okay. So let's make this now a little bit trickier. I'll give you something you haven't seen. So, male student gets A. So what I mean here, just to be clear, the probability that if you take a male student, he'll get an A. So you already know it's a male student. You've picked a male student out of the class. What's the probability he'll get an A? Yeah, well, write it as a percentage there. Now, just the other way to write this, I would rather write it like this, that it gets an A from the males. So again, you know it's a male student. Or another way to write it is probability of an A given that it's a male then. Yeah. So we're making the point here that you already know it's a male student. What's the probability to get an A? So what do we got here? 8%. Some people say 8. Okay, let's see what it is. So what do we have on the bottom?
14.
Is it 14 on the bottom? 24. There's 24 males. And of those 24 males, how many got an A? 4. Yeah, so what is that? 2 over 12, isn't it? Yeah, 1 over 6. 16.67, about 16%. Nearer 17%, isn't it? Yeah. 17%. Yeah. Okay, I'll give you another one that's like this. So D, we'll look at the other way. So what's the probability that the student is male, given that they got an A? So in other words, you take an A grade student, what's the probability that they're male? Is that the one you're thinking of? Yeah? Yeah. What is it? The probability that the student is male, given that you know they got an A. So how many A students are there? 14. So you choose one of these 14 students. When you choose one of these 14, how many of them could be an A student? 4. 2 over 7 then for this one here. What's that, 28%, isn't it? So does it round up to 29?
Yeah.
I'm sorry, I get a bit confused. Isn't it basically the same question?
Oh, everything in maths is basically the same. What's your question?
Serves is talking about A given back male,
Male.
male given back, they got an A.
Yeah, it's reversed. Here, you take a male student and you're asking what's the probability that he will get an A, whereas here you take an A grade student and ask what is the probability that they are male. From the A grade students.
From boys and girls. Like
Yes, yes.
Got it.
Okay, another one like this, yeah?
Yeah.
Let's make it a little bit trickier now. Let's say probability that the student will get a B. Yeah, let's just do another one like this. A B given that they are female then. Try this one then. Back to the table. Zoom out more. Can you still see? Yep.
Got it.
Yep. 6. You know that they're female, so there's 26 of those. And of the 26 females, how many of them? 6. So 6 over 26 then. 23%. 23%? Yeah. Okay. Can I go to another example now? Yeah. Okay. Scrolling down. Have you done any probability? No, probably not yet in biology. You haven't done genetics yet, have you? No. Have you done any probability or number questions like this with Colin? You've done it in high school, but what about this year? No? Okay. So we'll just make up an example here. So again, we'll make it a biology example. So and then male or female, and then 2 here. Okay, so male and female. Then we can say something like they have a particular genetic disease maybe, and then they don't have it. So something like this, yeah. Oh yeah, no, but what I'm saying is in probability you can also show the not by putting a little tick beside the D. And I know in genetics the recessive gene is lowercase then, yeah. But because it's probability I'm going to use the little prime, yeah. So this means they have the disease and this means they don't. So of course you know from biology that maybe gender plays a role, particularly in genetic disease. So in this, hemophilia, yes, that's right. It affects men more than females. Are females only carriers? Or yes, okay. So we won't look at an example like that because I want to pick a disease that affects both men and women, but maybe affects men more than women. Cystic fibrosis, yeah. So is it more likely for men to have it than? Come on, you're all biology students. Can you name me one disease that affects men maybe twice as more as women or something like that?
Prostate cancer.
Now Nathan, I'm no biology student, but I know that one, yes. So give me a disease that does affect both. I'll make it more interesting that colour blindness, okay. It affects both genders, yes? Yes, but it affects who more? Men much more than women. Okay, what, twice as much, 10 times as much? No, we'll just say twice as much or something like that. Okay, so let's fill out this table and we'll put in some realistic numbers. So let's say 20 men have the colour blindness disease, and we'll say now 40 here. Now I know we said men is affected more, so we say 40 here. And then don't have the disease, we'll say 5, and here I would say 40. Okay. So, hold on. What I want you to calculate is calculate the probability of having the disease if, given that they're male, and then probability of having the disease if you know they're female. So I'm looking for probability of the disease. Now, I want to show you a little bit of shorthand. When I write this vertical symbol here, I don't know if anyone seen it, that means given that, or if. So probability of the disease if you know that they're male, so you know this for a fact, and then the second one, probability that they'll have the disease if, or given that they're female, so you know that they're female. Okay, so let's have a look at these two here.
What was the name again?
What's that?
Fine, what was it again?
Not the disease. So before you even start, you should calculate totals here, okay? Yeah, so here, 25 here, 80 here, 60 here, 45 in here, 105. Right, if they're male, there's only 25 of those. What's the probability that the disease will be present? 20, which is 80%. And then female, there's how many? 80 females. And how many have the disease? 40, so as a percentage it's 50% then. So at first glance, you might say, this disease is more common in women than it is in men. But of course you realize, well, these are not percentages. These are numbers. And the reason this is, why is this bigger than this? Well, it's only because in my sample I happen to have more women than men. But as a percentage, the disease is more prevalent in the males in the sample than in the females. So you just have to be careful with things like that, reading these tables, okay? Until you have percentages, you can't really make any statements until you have percentages. So the other one I want you to do is the opposite. I want to know what is the probability that they're male, given that they have the disease, and what's the probability that they're female, given that they have the disease. Now before you start, before you start, it's good to have a good instinct for if the numbers, what the number should be. So, should this be a high number or a low number? The probability that they'll be male, given that you know they have the disease. It should be high, because we know this disease is more prevalent among men than women. And likewise, this should be low, or at least lower than this one. Okay, now you can calculate. Okay, you have this one done? Yeah? Okay, so how many people have the disease here? 60, and of them, how many are men? 20. So it's 33%. Yeah. Now, we said that should be high, but really high compared to what? So really we want this one just to be lower than 33. How many have the disease? It's still 60, isn't it?
Yeah.
60. And how many of them are female? 40. Did I add this in right? 60 and here 20, and here, yeah, so what's this, 67%?
You have a larger sample space.
So the reason is, yeah, what was it?
You have a larger sample space.
Yeah, it was only because in my sample, it's not representative. We have much more women than men.
You need to see it in the sample space then it will show.
Yeah, well, this is what we'll have a look at next. So if we imagine that in real life, the population will be 50% male and 50% female. So it would not be like this. Again, this is the point I was trying to make earlier. Sometimes these things aren't what you expect when you just look at them. So because we saw here, if you're male, you've got 80% chance, and if you're female, you've got 50% chance. So in the general population, if I take out a man, he's more likely to have the disease, yes? And if I take out a woman, she's less likely. If I take out somebody who has the disease, are they more likely to be male or female? Male. But here they're more likely to be female, and that's only because so it's not representative. There's so many more females than males. That there's so many more females with the disease than males. Only because there's just so many more females. So again, I'm trying to make the point that these are not, I know they look simple, but they're definitely not obvious. And there's a very, very important biology example I want to do with you, which is actually the last question of the worksheet, which I'll flick up on the screen here, and we can do this one together. And again, this one, it really demonstrates my point here. So if we have a read of this one. So this is if you can see that, a typical, what you might call research type of question. What you have here is 700 patients. And by the way, this is real numbers here. 700 patients, and they were treated for kidney stones, and you all know kidney stones. The kidney stones can basically be small or large. So in other words, you have two severities, levels of severity. You can either have small kidney stones or large kidney stones. The patients were treated with two treatments, A or B. Answer the following questions. Okay, so the first one, how many patients were treated with treatment A? So here, these were the patients who were successfully treated with A, meaning that they were treated with A and their kidney stone problem went away. And these were people who were treated with A but were still sick. And these are ones that had small and these ones who had large. So how many patients were treated with A? What do I add together? These four get added together here. Okay? So that's the first thing, if you can write that down. Now, I won't write that on the screen because that is straightforward. What do you get when you add those four together, please? $350. The next question, how many were treated with B? If you can add those together. $350. No, not necessarily. No. Because the reason they're both $350 is only because whoever was given the treatment decided to give half the people treatment A and half the people treatment B, which of course is realistic, but it didn't have to be that way. They could have gave more people A than B. Yeah, if you're trying to compare the treatments, you should make them the same. Yeah, but it didn't have to be the same. It just should be the same. Okay, so C. What is the probability of being successfully treated with treatment A? Now, I remember I didn't say if you had large or small kidney stones. I just said successful treatment with A, regardless of who you are. Well, how many people were successfully treated with A? There was 81 with small stones and 192 with large stones successfully treated, right? And in total, how many people were treated with treatment A? 350. So what is that as a percentage, please? 78%. Okay, do the same thing for D now. So how many were successfully treated with D? B, sorry. 234 plus 55 over 350. So what percentage do you get here? 82.5, so 83% then. Okay, so if I just switch here. So to answer part E now, of the two treatments A and B, which has a higher success rate? In other words, which is more successful in treating kidney stones? B and A, so it looks like if you were treated with A, what's your probability of being cured? 78, and if you were treated with B? 83. Okay, so the next one now. What is the probability of being successfully treated with treatment A if you have small kidney stones? So if you're a patient with small kidney stones, what is the probability of success now? 81 over 350. And then what's G is if you, with treatment B, if you have small kidney stones. Okay. What was the first percentage, please? The first one was 81 over, sorry, if you had small kidney stones, it was 81 over 81 plus 6. Sorry, we're back to F. I didn't write F up. It's 81 at the top, because that's how many people were successfully treated with small kidney stones. Why have I got 81 plus 6 on the bottom instead of 350? Small kidney stones. I said at the start, I'm looking at people with small kidney stones. Yeah, so that's why it's only 81 plus 6. Not everybody, just the small kidney stone people. So if you have a small kidney stone, what is your probability of being successfully treated now?
81 over 87.
Yeah, 81 over 87, which is 93%. Okay. G is, what is your probability of being successfully treated with B if you have small kidney stones? So what is it with B? Successful treatment with B, 234. And how many people have small stones there? 234 plus 36. What percentage? 87%. Okay, so back to my workings here. So, is it 87? Yeah. Okay. If you have small kidney stones, which is better treatment for you, A or B? So if you have small kidney stones, you want to go with A. Yes? Okay, let's have a look at H now. That was H, isn't it? Is it not this? 87? 234 over 234 plus 36. Yeah, this is right? Okay. So, answer for H is treatment A is better. Okay, I now. So can you all do I and J? It's the same thing, except this time with large kidney stones. So what is the probability of success with large kidney stones for each? Yeah? Huh?
Yeah.
Relax.
No, it's
210. Is it in Sylvia's office? Where? Yeah. We'll finish this up now. Give me the two answers for I and J. 73% for I, yeah. And then for J? 69%. So now we can answer K. If you have large kidney stones, which treatment is better? A is better. Yeah, no, this is what we're getting. Get a higher success rate. Now, so if you have large or small kidney stones, and you're going to have one of them, which treatment is better? A is better. Now, what was your answer for part E? Which did you say was better? B was better. No, don't practice 60 seconds for you to have a profound mathematical moment, please. Yes. Can you feel it? Yes. So, in part E, you're ruining the moment. Please, stop. Stop. Because I'm just going to delay everybody as I'm waiting for people's attention. Right. So, in part E, we said... You're not listening, and you're just delaying everybody. And they want to get their EAP done. So just listen. Thank you. 2. To who do you think?
Yeah, I'm listening to you, but what's the EAP thing?
Right, so part E, we said B is better. Why did we say B was better? Because B had a higher success rate. Now, when we looked at them individually, small kidney stones and large kidney stones, we concluded that A is better every time. So A is better. So we have a contradiction. B is better from our earlier calculation, and A is better from our later calculation. Both of them can't be right. One of them has to be better. Average them though. One of them is better treatment, but the question is which one? Is it A or is it B? This is to think about. Why A? Does anyone know? We're getting there, yeah. But why is the results contradicting? This is something to think about. Yeah, but why should that matter? You know, if I look at a treatment for this whole class altogether and find that treatment A works better, but then if I look at the men separately and look at the women separately, and in each case B works better, that seems like a contradiction. Yeah. Okay, moment over. Now you can go. So, try to finish these at home, okay? Find out next.